Okay, when we look at the electron configurations of atoms, we're going to be looking at these with a number of different ways. First of all, I'm going to say for the electron configurations of atoms, we're looking at the ground state,
Ủa,
which
sao
means
chị
the
tưởng
most
là em?
stable. Okay, I'm going to go ahead and mute you on.
Tại muốn ăn
Yeah.
thôi.
Let me mute myself.
Okay. Okay, so we're looking at the ground state, which is the most stable. And there's the SPDF notation. And then there's the noble gas notation. And both of these, then there's also the orbital box notation. I'll get into these in just a minute. Now, for the electron configuration of atoms, we want to show the shell, subshell, and sometimes the orbital for each electron. We're also going to follow something called the Aufbau principle. Which is the filling order. And we're also going to follow something called Hund's rule, which says you fill the most stable orbital first. Okay, so that's kind of the background. Now, as far as stability of shells go, we know that a 1 is more stable than a 2 is more stable than a 3. So this is the principal quantum number n, and this is the way it goes. So the way we kind of draw those is if you have a nucleus, whoops, that's a 2. 1 is more stable than 2 is more stable than 3. These are not supposed to be orbits, they're supposed to be spheres, okay? But I don't want to draw a sphere, it's too hard. So when we get to the stability of subshells, an NS is more stable than an NP is more stable than an ND is more stable than an NF. So N is the particular shell. So when we take a look at different shells, like at N equal 1, there's only a 1s subshell. So it doesn't have to compete with the 2p, there's no such thing. For N equal 2, there's a 2s, which is more stable than the 2p. And there's only 2 subshells. For the third shell, there's 3 subshells. And the 3s is more stable than the 3p, which is more stable than the 3d. For the N equal 4, there's a 4s, a 4p, a 4d, and a 4f. And for N equal 5, there's a 5s, 5p, 5d, and there is a 5f. But for N equals 6, there's a 6s, there's a 6p, and there's a 6d, and that's it. There's no 6f on the periodic table. So if you look at the first 4 shells right here, the shell number equals the number of subshells. N1, 1 subshell, N2, 2 subshells. Now, the reason that these are not equal, so 2s technically could be equal to 2p because they're both in the second shell. There's a reason that they're not equal and why the 2s is more stable than the 2p. So I'm going to explain that to you very briefly. You should read about it in the book, but it has to do with something called effective nuclear charge. Now, nuclear charge is the same as the number of protons in the nucleus. So the symbol has Z in it because that's the number of protons in the nucleus. But effective means that it is not equal to Z. So if we look at a lithium atom, it will have electrons in the first shell and the second shell. So if we look at the lithium atom, remember for n equal 1, there's 1s. For n equal 2, there's 2s and there's 2p. So for a lithium atom, it has 3 electrons because its atomic number is 3. So according to the Aufbau principle and Hund's rule, we're going to put the electrons in the most stable subshell first. And that's this one right here, the 1s. And the 1s has 1 orbital, so you can put 2 electrons in there. And then for the 2s or 2p, you're going to put the last electron in the 2s. So there's the electron configuration of lithium. But it could have easily been a 1s2 and a 2p1. So why is that not the case? And so we're going to take a look at that in just a moment here. It turns out that when you look at this 2s electron, so I'm going to draw the lithium nucleus here. And here's your n equal 1. And here's your n equal 2. And these are the 2 electrons in the n equal 1 shell. And here's the 1 electron in the n equal 2 shell. And we haven't decided yet. So for the moment, we're pretending we don't know whether this is a 2s or a 2p. We don't know, okay? But we do know that these are 1s's. Okay, now when this electron looks at the nucleus, which has 3 protons, what does it see? Well, when it's way out here, what it sees, the electron sees a +1 charge. So you might ask, well, how can that be? Well, this electron is pretty far from the nucleus, and it's pretty far from these electrons. So it can't really see these electrons and these protons individually. It sees the additive effect of all 3. 1, 2, 3. So when you add these all up, this is +3, this is -1, this is -1. That adds up to a +1 charge. Okay, so that's when it's in the far away from the nucleus. But if you remember, and you look at the radial density maps, here's a 1s and here's a 2s. This 2s electron can be closer to the nucleus than a 1s, okay? So before I go on, this is called screening, because these electrons effectively screen this electron from the nucleus. So here, imagine that this 2 electron is right here. It's right there, very close to the nucleus. In this case, you would see this. So here's your lithium nucleus with a +3 charge. And here's your n equal 2 electrons, or n equal 1, excuse me. And here's your n equal 2. And this is the N equal 2 electron. Do you see how it's a lot closer to the nucleus than these 2 electrons? So here, the electron sees a +3. So they call this penetration because it gets inside of the screening of these 2 electrons. Okay, so the result is that the electron doesn't see a +1 charge and it doesn't see a +3 charge because the electron could be anywhere underneath this graph. And so we have to have a weighted average. And if we take a look, it looks like the electron usually is outside of those other 2 electrons. So its effective nuclear charge should be closer to 1 than it is to 3 because it's really not inside too often. So there's some effective nuclear charges that are given in your book. And here, if you have a 2s electron for lithium, that 2s electron has a effective nuclear charge of about a 1.28. Now, if it were a 2p electron, it'd probably be more like a 1.4. So why are these numbers different? And the answer is basically due to this picture here. The 2s can penetrate better than the 2p. If we were to draw the density map of a 2p, the density map of a 2p would look more like this. I'm going to use a different color. So a 2p density map would look more like this. That's the 2p. And you can see that it doesn't penetrate. It doesn't get close to the nucleus as well as the 2s. So because it doesn't penetrate as well, oh, I'm sorry, this shouldn't be a 1.4. This should be more like a 1.2. My bad. Sorry about that. So because this doesn't penetrate as well, spends more time on the outside, it's going to be closer to 1 than the 2s. So why is this important? It turns out that larger Z star means a more stable electron. Because that Z star is its ability to hold on to the electron. And if you can hold on to the electron better, it's more stable. If you can't hold on to it as well, it's less stable. So this is the case throughout the whole periodic table, that if you look at a 2s versus a 2p, a 2s is going to be more stable. Let me show you some numbers here that are from the book when we look at 2s versus a 2p. So here's the atom, lithium, boron, carbon, nitrogen, oxygen, and fluorine. And here's Z star for a 2s electron. And here's Z star for a 2p electron. Now, these numbers here that I'm writing on aren't numbers for you to memorize. They're just numbers for us to understand the trend. So here, I'm going to put Z over here, the number of protons in the nucleus. This is 3, this is 4, this is 6. Oh, boron is not 4, boron is 5, I'm sorry. Nitrogen is 7, oxygen is 8, and fluorine is 9. Okay, and here are the numbers for carbon, 3.22 for a 2s electron. Then we have 3.85, then 4.49, then 5.13. Now, when we look at 2p, they don't actually give a number for 2p here, but for boron, it's a 4.42. So here, this larger number on means that this particular subshell is more stable than this one. And when we look at the sets of numbers throughout, you'll find out that they're always more stable in the 2s. This one, you can see there's not much of a difference, but there is a difference. Okay, more stable because it has a higher Z effective or larger Z effective, whichever word you want. And notice that the Z effective is always less than the actual Z because of screening. So the Z star is always less than Z due to screening. So we could build a similar chart with a 3S, a 3P, and a 3D. And we could do the same thing with a 4S, a 4P, a 4D, and a 4E. And we'd find out that an NS is more stable than an NP, is more stable than an ND, is more stable than an NF. Okay, so going back to the electron configuration of atoms, we now know the stability of the different subshells. So if we look at n equal 1, there's a 1s. For n equal 2, there's a 2s and a 2p. For n equal 3, there's a 3s, 3p, 3d. For n equal 4, there's a 4s, 4p, 4d, and 4f. So if we put these in order of increasing stability or increasing energy or decreasing stability, 1s is more stable than 2s. 2s is more stable than 2p. 2p is more stable than 3s, and this is the order you would put them in. Oops. Let's wipe that out just to make it a little neater. And this would go on for shell 5, shell 6, and shell 7. And what you're supposed to notice here is that all of the subshells in the first shell are more stable than all of the subshells in the second shell, which are more stable than all of the subshells in the third shell, which are more stable than all of the subshells in the fourth shell. Now, it's also important to know that when you have an S subshell, this has one orbital, which according to the Pauli exclusion principle, it says every electron has to have a unique set of quantum numbers. This can have 2 electrons maximum. A P subshell has 3 orbitals, which means you can have 6 electrons maximum. And a D has 5 orbitals with 10 electrons maximum. Notice that the number of electrons is double the number of orbitals. And we say maximum because it doesn't have to have 10. It can have up to 10, but that's it. So we can use this to kind of figure out the electron configuration of atoms. So let's try and use this to figure out the electron configuration of hydrogen. So hydrogen has 1 electron. So where do we put the electron? We put it in the 1s because it is most stable. So we say 1s1. And for helium, which has 2 electrons, we say 1s2. And for lithium, which has 3 electrons, we say 1s2. We can't put all 3 into the 1s because this 1s has 1 orbital and you could only put 2 electrons in there maximum. So we have 1 more electron to put into this configuration, so we put it into the 2s. So what you're supposed to understand about these electron configurations is that the number in front is the shell. The letter is the subshell. And the superscript is the number of electrons in the subshell. Okay. Now, this is called the SPDF notation, but there's also something called the orbital box notation. So for these, here's what the orbital box notation looks like. This 1s is one orbital, so you draw this, and the 2s is one orbital, so you draw that. Now, when you put the electrons in the orbital boxes, you don't put them in as E's, you put them in as arrows. So here, you put the first arrow up and the first arrow down because these have different spin. So the one going up is a +1/2 spin. The one going down is a -1/2 spin. Oops, and I made a mistake because hydrogen doesn't have 2 electrons. Hydrogen just has 1 electron. Now for helium, it's going to look like this. And I'm not even going to draw the 2s because there's no electrons in it. For lithium, it looks like this. And by convention, we always put the first electron in, spin up, arrow pointing up. So that's the SPDF notation and the orbital box notation of the first 3 elements. What we're going to do here on is we're going to do some more elements. So remember, we have 1s2, 2s2, 2p6. Oh, excuse me. I'm going to get rid of that. We have 1s, 2s, I got to tell you, it takes a lot of talent to say 2s and write 2p. It's hard to do. So I'm going to write and not talk for a little while. So that's the order of stability. And remember, this guy can hold 2, this guy can hold 2, this guy can hold 6, this guy can hold 2, this one can hold 6, this one can hold 10, this one can hold 2, 6, 10, and 14. So that's how many electrons it can hold. So let's do a few more atoms. So after lithium, we have beryllium, and then we'll do boron, and then we'll do, what's after boron? Carbon, and then nitrogen, and then oxygen, fluorine, and neon. Now the Z on each of these, the number of protons is 4, 5, 6, 7, 8, 9, and 10. That's the number on top of the symbol of the element in the periodic table. And the number of electrons is going to be equal to the Z. So for the SPDF notation, we have to put 4 electrons into this chart. So how many can we put into the 1s? 2. How many can we put into the 2s? 2. Okay. Now for boron, we do the same thing, only we have 5 electrons. How many can we put into the 1s? 2. How many can we put into the 2s? 2. But we still have 1 more electron. Where do we put it? We put it into the 2p. So 2p1. Now notice here, we don't leave this number off. We always put a number there to tell you how many electrons are in that subshell. So what I want you to do is I want you to take this carbon here take these 6 electrons and put them into these subshells, write out the configuration, and when you get what you get, just let me know. Just give me a thumbs up that you're done. I'll show you my answer and you can see if you did it right, okay? Okay, good. So with 6 electrons, I'm going to put 2 into the 1s. I'm going to put 2 more into the 2s, and I have 2 left over. I'm going to put both of them into the 2p. Okay, so what I want you to do now on is I want you to do the rest of these: nitrogen, oxygen, fluorine, and neon. Well, actually, do you feel okay with these? Or do you want some more work on this?
I feel good with this.
Okay,
It's good.
then
Yeah.
if you feel good.
We
I
can
want
skip
you to fill the rest of these 4 out very quickly.
Okay. Yeah.
And give me a thumbs up when you're done, okay?
Yeah, sure.
855.
Okay, so I'm going to fill mine out, and then you're going to check yours as I fill mine out. 1s2, 2s2, 2p, 3. And notice 2 plus 2 plus 3 equals 7. So it works out. 1s2, 2s2, 2p4, 1s2, 2s2, 2p5, and 1s2, 2s2, 2p6. So those are the SPDF notations. Now let's look at the orbital box notation. Now here, what I'm going to do is instead of making boxes, I'm going to make lines. So I'm going to do a 1s, a 2s, and a 2p. And the reason I'm making lines is because it's just a lot faster. Now you might be wondering what's going on with the 2p. Well, the 2p can hold 6 electrons, which means it has 3 orbitals. Each line is a box, and therefore, I'll go ahead and put the boxes in for this guy. And therefore, you have 3 orbitals. So when we put the electrons in, we do this. For beryllium, 1 up, 1 down, 1 up, 1 down. Now for boron, we do this: 1 up, 1 down, 1 up, 1 down, 1 up. So give me a thumbs up if you understand that this is a 1s orbital and so are these. This is a 2s and so are these. This is a 2p and so are these. This is a 2p and so are these. This is a 2p and so are these. Each box is an orbital. Are we good? Okay, thank you. Now for carbon, we have to make a choice here. For carbon, do we put the next electron next to this one going down? That's what I want to do because it looks nice. 1 up, 1 down, 1 up, 1 down, 1 up, 1 down. But that's not the case. The next one goes here. So what's the explanation for putting this one here? And the answer is that these orbitals are all the same energy. They're all the same energy. So that's why we fill this guy up before we put him into here, because these orbitals are more stable than these. But these three, they're all the same stability. There isn't one that's more stable than another. Secondly, electrons have a negative charge. If I put 2 electrons in the same orbital, is that going to be as stable as putting 2 electrons in different orbitals? And the answer is no, it will not be as stable because the electrons repel one another. So rather than stick both electrons in the same room, put 1 electron in one room and 1 electron in the other room, and they're more stable. It's kind of like if you have kids and you have 2 bedrooms. Let's say you have 2 kids and you have 2 bedrooms. You know, when they're young, you can put them both in the same room, but when they reach a certain age, you're going to put them in different rooms because they'll fight all the time. So do you kind of understand the analogy for putting the electrons separately instead of together? Good. Okay, so here I want you to fill the electrons in for nitrogen. Give me a thumbs up when you're done. Okay, so you're going to put 1 up, 1 down into the 1s, 1 up, 1 down into the 2s, 1 up into the 2p, 1 up into the 2p, and 1 up into the 2p. Okay, so if you feel confident, do you feel confident now with these? Okay, fill the rest of these out. Do oxygen and fluorine. And neon.
Yeah, I'm done. This just like flashback stuff in high school, so I can't remember what I said.
Okay, good. You know, I'll be honest with you, on everything that we do in this class should be review from high school.
Yeah, I mean, I don't know. This stuff is like just flashback me.
Yeah. Now, some of the stuff we review is easy, some is hard.
Yeah.
And we do go into a little more depth usually. Okay, so these are the electron configurations. Now, let's talk about magnetism. These are in the notes, but I'm just going to say it. You have 3 types of magnetism. The 2 that we want to be worried about are something called paramagnetic and diamagnetic. Paramagnetic is a material that's attracted to the poles of a magnet. Diamagnetic is you're repelled from the poles of the magnet. Turns out for something to be diamagnetic, all the electrons have to be paired. So this is diamagnetic. So this is neon is slightly repelled from the poles of a magnet. Is there anything else here that's diamagnetic? Right up
Is
here.
that the beryllium?
Beryllium. That's right. And everything else has an unpaired one. It doesn't matter how many are unpaired, you just need one. And it's then paramagnetic. Now I'm getting lazy here, so I'm not going to write this word out again. I'm just going to put para, 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 para.
So the paramagnetic is they go together, right? They come together with magnet,
Yes,
and dia is they repel.
right.
Yes.
So para is attracted to a magnet.
Okay, that's right.
So come together. That's correct. And dia is repelled. Okay. So we have enough information to go ahead and start doing some problems. And I will show you one more thing though, before we move on to the problems. And that's this one right here. I want to get the electron configuration of iron. So iron has a Z of 26, so it has 26 electrons. And we know that it's 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, and so forth. So if we follow this method of stability, this is what we get. 1s2, 2s2, 2p6, 3s2, 3p6, 3d, and let's see. So far, we've got 2, 4, 10, 12, 18.
32.
So we need 8 more. So we
Eight
get
more,
3d8. So this would be the electron configuration if we just follow which orbital or which subshell is more stable. And this is wrong. So when we fill, so the filling order works up to, let's see, works all the way up to calcium. Then we need to change. Then we do something else. So here, this works all the way up into calcium. And so that means it works all the way up into right here.
Oh, I see. I see.
And actually, I shouldn't say works all the way up to calcium, works all the way up to argon. And then we have to do something else. So that's why I have this drawn here. Because this is what we're going to use for getting the electron configuration. And it gives us a very reasonable electron configuration. This right here is called the S block. So that means that each one of these little rectangles represents a subshell. And this is the 1s subshell. This is the 2s, 3s, 4s, 5s, 6s, and 7s. This is also part of the S block. But the rest of these are the P block. And this is the 2p subshell. This is the 3p subshell, 4p, 5p, 6p, and 7p. This is the D block. And this is a 3D, 4D, 5D, 6D. And you'll notice that the S block starts with 1. E block starts with 2. The D block starts with 3. Well, down here, this is the F block. So what do you think the F block starts with? If this starts with 1, and this with 2, and this with 3, what does the F block start with?
4.
4. So if we do this, we can then do iron. So here's iron.
Mm-hmm.
And here's how we get the electron configuration of iron. We start here and we go through the subshells.
Yeah.
So can you see that if we start here and then we go here and then we go here and then we go here, we read from left to right and we look at the subshells that we go through to get to the element. So do you see that we go through the 1s?
Yeah.
And how many elements do we go through?
One. One. Right?
2. We go through
2.
this one And this
Right.
one, that's 2 elements, right?
Yep. Oh, so 2 electron.
So 2s what? How many elements do we go through?
2?
How many elements in that box?
Two. Definitely 2.
How about the 2p? How many elements in that box?
6.
That's
I
right.
know.
That's kind of
I
corresponding.
didn't finish the sketch
How many in
note.
this 2s or 3s?
2.
I didn't finish the sketch note.
How many
You
in the
know, I
3p?
did ask this. I literally searched
You say P3? Oh,
3p.
6.
the
6.
last quiz.
How many in the 4s?
2.
2. How many do we have to go through to get to iron?
Like,
How many
This is so
boxes to get to
6.
iron? 6. So 6. Now, when we add these up, do you see that the
those
first
words
3 are
so
10,
confusing.
the second 3 are 10, and the last
Uh-huh.
one is 6 for 26 electrons, which is what we should have.
Okay.
Now, this is not correct. We have to do one thing to it, and that is to put these in order.
Oh,
So I'm gonna
that's
do
why
a little-
I'm wondering.
So to put them in order, this is what we do. 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, 4s2.
The sketch
Oh, okay.
notes.
So this is correct. Okay, so here's what I
Yeah.
want you to do you can go ahead and mute me if you want. I want you to get the electron
I did, but
configuration
I don't-
of cobalt. Get the electron configuration of cobalt. Actually, let's not do cobalt. That's too close to iron. I want you to get the electron configuration of rubidium. Oh, ruthenium, not rubidium. Rubidium's over here. Get the electron configuration of ruthenium. Write it all out. And when you're done, give me a thumbs up. This is going to take a little bit of time. Okay, so for ruthenium, you would read 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, and 4d6. Now, that's before we rearrange it. So here's my little symbol for rearrange. 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d6, 5s2. So we rearrange it so we put the 1s together, the 2s together, the 3s together, the 4s together, and the 5s together. All right, on? Okay, so that's how
Yeah.
you would do
Wait,
ruthenium.
are you in this class? Are you?
And I'm going to show you one more really tough one, okay? So the next really tough one is going to be let me make sure I pick one. So we're going for a reasonable electron configuration. I'm going to pick this guy here. Oh, before I pick a really tough one, I want to show you another way to do this. here, what is the electron configuration of this element here? So this element here is krypton. So if we look at krypton, and I'm just going to jump to krypton, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, and 4p6. So this is what it would look like after you rearrange it. So that's krypton. And krypton is a noble gas. You'll notice that when we look at ruthenium and you look at krypton, their electron configurations are exactly the same up until the last two. So another way to write ruthenium is this way. (4d6, 5s2). Now I'm going to show you a quick way to get this electron configuration. So for these elements that are really high up in the periodic table, like ruthenium, we can say, okay, what is the previous noble gas? So for ruthenium, it's krypton, right? So that's what you start with. And then you start right here and you go to here. So what do we write next? We write 5s2 and then 4d6. And then you rearrange. So what is my little pig? I call this a pigtail because it looks like a pig's tail. So what does my rearrange mean? It means rewrite it so that the 4s come before the 5s. And that's the same as this over here. Are you kind of with me there?
Yeah.
Okay.
We're getting there.
So now let's do something really radical. Let's do this guy right here, which is cerium. Okay. So we want to look at the periodic table and see which one is the previous noble gas for cerium. So cerium, if we take a look at the number, it's 58. So the previous noble gas is going to be right here, xenon. And let's see what we get for cerium. For cerium, we're going to start with xenon. And then the next thing we look at is the 6s. And we go all the way through it. But cerium is 58. This guy is 57, lanthanum. And this guy is 72, hafnium. So the pathway to cerium doesn't go through hafnium, it goes through lanthanum and then down to cerium. So what do we do here? Well, we say, since lanthanum is in a 5D and it's only the first element in the 5D, we say 5D1. And then we go down to cerium and we say 4F1. And then my pigtail means rearrange. So we get xenon, 4F1, 5D1, and 6S2. So cerium is some serious stuff. And then here, if we do hafnium, what is hafnium? Well, let me show you what hafnium would be. So for hafnium, we would also start at xenon. We would go through the 6s and call that 6s2. We'd hit lanthanum and say 5D1. We'd go down. We'd go down through this whole F block and call that 4F14. And we'd come back up to hafnium, which would be 5D1, because it's the second element. So what we do here is we're going to rearrange and combine. So we're going to have 4F14, 5D2, and 6S2. So did you kind of get that on or no? Give me a thumbs up if you kind of get it.
Yeah, I kind of get it, but I have a question
Yeah.
about the F block. Is it
Yes.
supposed to be 5 and 6?
No, the F
I'm
block
kinda
is
confused.
4F and 5F.
Oh, because like it start on LA 57.
Yeah. Well,
So I thought it would be like in the 5 row.
no, it starts with an F because the fourth shell does have an F subshell.
Oh
So
yeah,
this
yeah,
is the
never
F
mind.
block. It has to start with 4. And so
Yeah.
that's why it's important to remember this starts with 1, 2, 3, 4.
Yeah, yeah. And 6 doesn't have a F block, right? F, so
No, you can
yeah,
see
that's why I can
5F, there's no 6F.
yeah, that's why I
So
go for
where would the 8S be? This would be 8S. This would be 7D. This would be 8P. And this would be 6F if we had elements that we knew about, but we don't. So we
Yeah.
don't write them in. Does that kind of make sense?
yeah, yeah.
Okay, so you've learned a lot about electron configurations. And you know what? Since you have kind of a mastery of this already, we won't bother with this for right now. Okay? Or do you want to try some of these? Up to you.
Yeah, I'll try some.
You want to try some?
Yeah, why not?
Okay. Write the electron configuration for magnesium and argon. So now I've taken my periodic table away, and you're going to have to look at your periodic table inside of your book or some other periodic table that you have. Do you have a periodic table nearby?
Yeah, yeah.
Good. So what is the electron configuration for magnesium? They want SPDF n orbital box. Tell me when you're done.
Yeah, I think I'm done.
Okay, great.
Nitrogen dioxide.
So here's my tiny little periodic table. So I'm going to start here at 1, 1s2, 2s2, 2p6, and 3s2. And I don't need to rearrange because it's already 1, 2, and 3. The box notation is going to look like this: 1s, 2s, 2p, and then 3s. So 1s looks like that. 2s looks like that. 2p looks like that. And 3s looks like that. Is this paramagnetic or diamagnetic? Dia.
Is dia.
Okay. Now how about argon?
Oh, God. Let me see. Yeah, I think I sort of got it.
Okay, so argon looks like this.
Yeah.
Hi guys.
Okay. The other thing they ask is what is the relationship between the atom's electron configuration to its position in the periodic table? And the answer that the book is looking for is, do you see how magnesium here is in an S block? And it's the second element in the S block. That's why it ends with a 3s2. And do you see how argon is the sixth element in the P block? That's why it ends up with 3p6. So that's what they're kind of looking for is, how many electrons you see from that particular block. And it depends on where the element is in the block. Like if you ended with phosphorus, it'd be 3p3. Okay, let's try another one here. Give the electron configuration of vanadium. And I'm going to amend this to give me the electron configuration using the filling principle, and then give it to me after you rearrange. I want both, before you rearrange and after.
Okay.
And just give me a thumbs up when you're done. Well, I don't know if it's getting sunny where you are on, but it's getting sunny where I am.
Mine's sunny too.
Makes me want to go outside.
Wait, do we have to write the box,
The
the
bottom
orbital
right.
box, most background?
No, they don't want you to do the boxes. It's too much trouble.
Okay, I think I got it.
Okay.
Okay, number 7. We low-key look fast, not even gonna lie. We're just reading the questions.
Okay, so this is before you rearrange it. And this is after. How'd you do, on okay?
Yeah. I'm good.
Okay, so here's the next question on paramagnetic or diamagnetic.
Is a para.
Yes, and you should notice that it's paramagnetic simply because of this guy right here. For something to be diamagnetic, all of the subshells have to be full. If they're not full, then it's paramagnetic. Really easy. Okay, how about this next one? Using SPDF notation and noble gas notation, write the electron configurations of. So when they say SPDF notation and noble gas, they mean start with the noble gas. So this is not two separate things. It's one thing. Start with the noble gas and do SPDF.
Wait, so we write the noble gas first, like the R something.
Yeah, so if you see strontium,
Uh-huh.
the previous noble gas is krypton. So for A,
Yeah.
you start with krypton.
Krypton. So the next one will be
Davis over here. Of course.
5s2.
Yes. And that's A.
Oh, so two of them are even one. So they just give like the direction to.
Yeah.
write
Hold on.
the-
So here, they're saying SPDF and gas notation. So when they write that, they're really saying do it one way, but don't do it the long way.
Oh, I thought like we have to do the notation and the
No.
gas like separate out.
No,
Oh,
they
okay.
just mean gas notation.
Oh.
How about B? Here's zirconium.
So it would be krypton 5s2
I've got neutrons.
4d wait.
Wait, I think I'm
Yeah,
wrong.
4d2 and then
And
we
then?
arrange it in order.
Different.
4 first and then 5.
Oops, I didn't rearrange.
Has anyone submitted yet?
No.
You should tell me the right.
You got it.
Okay, so.
How about C?
Everything else is right from what we said, and then number
C.
two.
Yeah, where was that?
So what's one? One?
Oh,
Okay,
oh,
I'm just gonna go.
oh, that's it.
Mm-hmm.
Okay.
So still would be krypton 5s2 and then 4d.
Number three is
Seven?
proton. Number four is protons and neutrons. Number five
1,
is
2,
protons.
3, 4,
Number six is
5,
the
6,
bottom
7.
right.
Very good.
Number seven is
And then
second.
rearrange
Eight
like the
is six.
second.
9 is neutrons, and 10 is protons.
Okay, so the next question for you on is your chemistry class harder or is your sister's chemistry class harder? If yours is harder, give a thumbs up.
Well, definitely yours. You just review, but like sometimes they give like more information that I cannot process. In
Okay,
one, so.
that's what I want to hear.
Yeah.
So is your sister going to take my class in the future?
I don't think so. She not really like chemistry.
Oh, she's not a
struggling
science
with
major,
it.
huh?
She sometimes she give like a crazy theories, and I kind of don't understand where she get that.
Okay. How about D for 10? It's right here.
Oh, SN. Oh. Well, still would be krypton.
Yes.
Right.
5s 4. Yeah, 4d6 and then 5p.
I think it's 4D10,
Oh,
isn't it?
10, sorry. Yeah.
You're thinking 4P.
Yeah.
Okay, and then what?
And then 5p2.
So 2P, 3P, 4P, 5P. So 5P2, and then what?
Rearranges as 4d10, 5s2, and 5p2.
That's right. So you've got this.
Yeah.
How about samarium?
SM. What's SM?
Down here.
Okay.
That's in the F block.
Okay. So SM. The group start with xenon, right?
What's that?
Are we starting with xenon?
Yeah, if you look at the number at the top here, the number at the top is 80 or 62.
62.
So xenon is 54. That's the closest to it that's below it. So xenon.
Yeah. So xenon is 5. So xenon 6s2, and then 5. Okay, this kind of confused me again. 5d 5d10.
5D1.
Up 1.
Yeah, because look at
Oh.
this element right here. That's number 57, right?
Yeah.
So that's only the first element in the D block. So 5D1, and then
Mhm.
58 is down here.
Mm-hmm.
So with my periodic table, this shouldn't be here.
Oh. No, okay, this one. So 5D1 and then we jump to the 4F.
Yeah.
Oh,
And how many
okay.
elements is samarium over? 1, 2, 3, 4, 5. So 4F, 5.
5F? Yeah.
Okay, and then we rearrange and we get xenon, 4F5, 5D1, 6S2.
Okay.
How about F?
GBT.
Ytterbium.
Where was that? Oh, it's on the F block. So still start with xenon, 6S2, 5D1, and 4F. 13?
Yes. That one's easy to pick as 13 because the last one is 14.
The last
right?
one, 14.
Does that make sense?
Yeah.
So 4F13, 5D1, 6S2. Now, I don't think that's the real electron configuration though.
Nah.
I think it's actually different, but this is what we call a reasonable.
Oh. Is that because of they too far away? They too radioactive? So
Well, it turns out that there's something called a symmetry argument for electron configurations that sometimes symmetry makes more of a difference. And so if you look at yttrium, ytterbium, which has an atomic number of 70, its actual
So-
electron configuration here is this.
what do you think?
So this is reasonable.
On the quiz.
And this is actual. Now, the reason is if you look at this 5D, do you see how that's not symmetrical? I mean,
Oh,
there's
can you
only
show
one
that a little
electron in there instead of 2. It's not full.
Oh yeah, that's why I
Yeah,
confused
this is
too.
13 and not 14. Just takes one more to do that. So we
Oh.
take this one electron and put it over here and make it a 14.
Is that the same with the samarium?
Let's see.
The
I
same
don't
case,
know
okay.
because here, if you take this guy and put it here, it's 4F6.
Oh yeah,
It would be
which
better if
is-
it were 4F7 because 4S7 means you have one electron in every orbital.
Oh
So I don't think it's the case for samarium, but it may
Yeah.
be. Let's see if samarium is what we got it to be. Yep, samarium does the same thing.
oh.
It does do the same thing. So
That does make more sense. In my opinion, because like you see the 5D the only one alone, and then
Yeah.
we jump to the 4. I'm like, why?
it's actually called a symmetry argument.
Yeah.
And when you have a subshell, like here's 5 orbitals. They say that this is not symmetrical.
Oh, can you scroll out the paper a little bit?
Oh, sorry. So when you have
That's fine.
5 orbitals, this is not symmetrical. So sometimes you would take a single electron here and stick it over here.
Oh, okay.
Now, you're not responsible for knowing which elements are weird. You're responsible for this,
Yeah.
getting
Okay.
a reasonable electron configuration.
Yeah.
If you take a look at this, it is reasonable. Between
Yeah.
these two, or I should say between these two, there's only one electron difference.
Mhm.
Only one electron is different. So out of the 80 electrons, 79 are correct and one's not. That's a pretty good record, don't you think?
Yeah.
Actually, I should say out of the 70 electrons, one is wrong and 69 are correct. That's pretty good.
Yeah.
Okay, well, we're going to call it here, all right?
Yeah.
And we'll see you Monday.
Yep. See
There's
you
a new
Monday.
lab posted. There's a all sorts of things posted.
Oh, okay.
The lectures, the lab, the homework. All of that's been posted. All right, On. You have a good weekend.
Yeah, you too. Have a
All right,
good weekend.
bye-bye.
Bye.